Controlled environment plant production engineering technology education modules are developed and presented by The Ohio State University, the State University of New Jersey, Rutgers, and the University of Arizona, with support from USDA, NEFA, through their Higher Education Challenge Grant program. This module will focus on weather station, and the module is presented by Dr. Peter Ling, who's an associate professor of The Ohio State University. By the end of this module, you will be able to first describe the benefit of utilizing an on-site weather station. On-site weather station is a weather station installed at a greenhouse location, sometimes is referred to as a greenhouse weather station. The second learning objective is that by the end of this module, you will be able to state key considerations of selecting a weather station site. A weather station is installed at a location where reliable information can be collected for greenhouse climate control purposes. The third objective is that you will be able to list key sensors and equipment of a weather condition. What is a weather station? Weather station is an observation post where weather conditions and the meteorological data are observed and recorded. Most people have a better appreciation of agricultural weather station from radio, television, internet, or other news resources. This type of information on temperature, rainfall, sky conditions are mostly based on field weather station data for macroclimate of a broader region. The focus of this learning module is at a microclimate level, where the information collection is for local greenhouse operation purposes. There are differences between site and equipment considerations of an agriculture field weather station for macroclimate information collection and a greenhouse on-site weather station that collects microclimate information. What is a field weather station? Weather information for agricultural applications include water usage, water resources, crop yield prediction, cultural practices, and long-term climate change monitoring related tasks. For water management, macroclimate information is used for estimating crop water use for irrigation scheduling, and for hydrological modeling for water availability and groundwater recharge. The macroclimate information is also used for predicting field crop growth, yield, and quality using degree day type of information. For pest management, the macroclimate information is used to assess disease pressure and to schedule pesticide applications. For example, rain and strong wind conditions are not suitable for spraying pesticides in the field. Another use of this kind of information is for urban landscape planning and management. For urban planning, the macroclimate information is helpful for selecting proper plant varieties for a given light, temperature, and the precipitation of a given region. Of course, the recorded climate information over time also can be used for climate change type of analysis. A greenhouse on-site weather station collects microclimate information. In contrast to the macroclimate information collected using a field weather station, only very localized spot climate is obtained, and it is used primarily for short-term interest rather than long-term climate pattern analysis. The microclimate information can be used for more efficient greenhouse indoor environmental control, for rain protection, so that dedicated greenhouse crops do not suffer rain damages, and for structure protection, so that timely measures can be taken to prevent structural damages under extreme weather conditions such as strong wind and heavy rainfall. Weather station provides valuable information that can be used for more effective and efficient greenhouse climate control. I will share some examples in this and the 4 following slides. The first 2 examples are related to cooling options. Among several cooling options, such as ventilation, evaporative cooling, and shade curtain application, which is the best option for a given outdoor condition? Here is an example of weather station reporting high temperature. Since the outdoor temperature is already higher than the desired greenhouse temperature, ventilation alone is not very effective. Alternatively, shade curtain can be used to reduce radiation load, and the evaporative cooling can be used to lower greenhouse temperature. The second example is the weather station reporting high humidity. Evaporative cooling works the best when outside humidity is low. Here we have a high humidity condition. Thus, we need to use other methods than the evaporative cooling to keep the greenhouse cool. In this slide, we will present heating and dehumidification related benefits. For heating, outside radiation level is a good indicator of what will soon happen in a greenhouse. High radiation indicates a greenhouse will soon be warmed up quickly by the sun. With the anticipated heat contribution from the high outside radiation, a control system can reduce heater output for more efficient heating operation. Our second heating example is how outside conditions may affect the decision of when to raise greenhouse temperature and open energy curtains in the morning. Under normal conditions, we will want greenhouse temperature to change from nighttime to daytime temperature and open energy curtain at the daybreak as soon as possible, so that plants can start photosynthesizing as soon as the sun is up. The heating and energy curtain operation decision can be affected by outside temperature and radiation level. For example, when outside temperature is extremely low and the sky is overcast, it may not justify to open the energy curtain to raise greenhouse temperature when the radiation level is low. Plants need sufficient light and certain temperature for efficient photosynthesis. When the light level is limiting, raising temperature alone will not improve photosynthetic efficiency. It is expensive to raise greenhouse temperature when outside is very cold. It costs even more trying to keep plants warm without protection of energy curtains. The next example is on the topic of dehumidification. Outdoor temperature and humidity information is important for the decision-making process of dehumidification operation. The most commonly used dehumidification method is by ventilation, that brings in drier and cooler outside air. The method is inefficient if the outdoor humidity is only slightly lower than the greenhouse humidity. The method is ineffective if the outdoor humidity is equal or higher than the greenhouse humidity. Knowing outdoor humidity before attempting to reduce greenhouse humidity with ventilation is important for efficient greenhouse climate control. The weather station information can also be used for protecting crops and greenhouses. For example, when rain is detected by a weather station, a control system can close roof vents to prevent crops from rain damages. Most of greenhouse crops are fragile and should be kept from rain. Another example is when strong wind is detected. To protect the greenhouse, one should close all openings, include ventilation inlet, louver, and the doors. Securing all openings and keep them tightly shut is the first step in protecting a greenhouse from wind damage. The effective force of the wind is greater when it is allowed inside the building. The wind on the outside puts a lifting force on the structure. The wind inside exerts force on the walls and roof. Secondly, increase pressure of air-inflated greenhouse to make it more wind resistant. Overinflation for a long time period, however, can shorten the lifespan of the polyethylene film. Reducing the air pressure back to normal pressure range after strong wind condition is necessary. Lastly, a negatively pressurized greenhouse can withstand strong wind better. Disconnect the arms of the motors on all ventilation inlet shutters and tape the shutters closed. Then turn on enough exhaust fans to create a vacuum in the greenhouse. This will suck the inner polyfilm tight against the frame, then make the glazing material more wind resistant. In addition to the benefits of using the weather station information for greenhouse climate control, that information can also be used for greenhouse structure and equipment diagnostics, using the information to detect conditions of greenhouse structure and equipment. Some of the examples include: inspect conditions of glazing material. Growers typically replace non-glass glazing materials such as polyethylene, polycarbonate, acrylic on a fixed time schedule every few years under normal conditions. Abnormal degradation of glazing material can be detected timely by having both outdoor and indoor radiation information on a more frequent basis. A second example is a performance evaluation of heating and cooling equipment. In this case, abnormal equipment operation, such as low efficiency operation, can be quickly detected using outdoor climate information and heating and cooling models of a greenhouse. For this type of diagnostic applications, outdoor radiation, temperature, and humidity information from an on-site weather station is necessary. The weather station information is also helpful for the detection of faulty sensors. In this case, abnormal sensor readings can be singled out by cross-checking expected readings in the sensor output. The expected greenhouse climate condition can be from a weather station and greenhouse energy balance models. Thus, deviated sensor can be uncovered if computer model prediction discrepancy exists. We have focused our discussion primarily on on-site weather station at a greenhouse location. There are indeed many potential benefits having a local weather station, as we have discussed. Here we will discuss how we can also use field weather station for better greenhouse climate control. Mostly, the information is used for anticipatory control to trigger earlier preventative measures using microclimate information. For example, in response to a tornado warning, one can prepare a greenhouse for severe wind conditions, as we have discussed earlier. The only difference is that the timing will be earlier, as the expected strong wind has not been detected by a local weather station. Next, in response to a cold front forecast, by anticipating larger heating demands in the coming hours or days, one can increase thermal storage in a heated floor or water storage tank if available. To get the most useful outdoor information for greenhouse climate control, one needs to assure that the weather station data is of high quality and a properly selected weather station location is very important. For macroclimate information using a field weather station, it should have a reasonable distance from the greenhouse in the direction of the prevailing winds. It should be installed at a distance of 4 times the height of the nearest tall object. It should be free from obstructions, shades, local sources of dust, air current, heat, and surface moisture. For an on-site weather station, stay clear of local influences for the most representative information. For example, ventilation exhaust temperature is not representative of outdoor temperature. Light reflection from shade curtain or glazing material can affect light level measured. In addition, local air turbulence can affect wind direction and wind speed measurements. What information a weather station collects? Typical weather station monitors wind speed and the direction, light intensity and accumulated light, temperature, humidity, precipitation, and rain detection. The sensors for the additional climate information listed below are useful, but generally only available through special requests. Barometric pressure change is an indicator of weather change. Decreasing barometric pressure indicates storms, rain, and windy weather. Rising barometric pressure indicates fair, dry, and colder weather. Next, the sky temperature or nighttime cloud-covered information is helpful for greenhouse heating requirement calculations. Weather station instrumentation include anemometer for wind speed and a wind vane for wind direction measurement. Anemometer installation needs to be in an open field at least 20 feet above the high point of adjacent open ground. Additional height adjustment is needed based on ground cover density. Rooftop installation needs to be at least 6 feet above the roof line. Anemometer poles should remain stationary during windy conditions, allows easy access to instrument, and provide a way to adjust height. For wind vanes, we need to ensure that the vane is properly oriented in relation to true north. The weather station also needs lightning protection. Mount lightning rods to attract lightning strikes away from anemometers and wind vanes. Similar to the wind sensor mounting considerations we just discussed, the light sensor location should avoid shades, light reflection from nearby obstructions, and as the light measurement is sensitive to horizontal level, the light sensor should be leveled. For temperature and humidity sensors, they should be installed in an aspirated radiation shield. Many factors such as buildings and trees and wind can affect how much precipitation a rain detector can collect. Proper placement is critical to ensure that rain sensor readings are an accurate representation of the actual amounts that have fallen. A rain gauge should be mounted at a minimum distance of twice the height of the tallest object in the surrounding area. Here is a review of what we have discussed on the weather station sensor installation. Take a careful look and think about what are done right and what improvements can be made for this weather station located in Ohio. Okay, let's go over the sensors mounted on the tower. On the top left is a wind cup anemometer. Next is a light sensor, then a rain detector, a wind vane for wind direction measurement, temperature and humidity sensors in a radiation shield, a data logger, and a solar panel. Even though we did not discuss data logger or a solar panel earlier, they are nice additions for a remote weather station. Did you find something needs improvement on this weather station? It is a big challenge to notice anything wrong with this weather station without knowing its orientation. As mentioned earlier, this weather station is located in Ohio, where the sun is always in the southern half of the sky. Thus, it is reasonable to assume that the solar panel is facing south. With that established, then we find the light sensor is mounted on the west side of the tower, and the wind cup anemometer is mounted further west of the light sensor. As the sun rises from the east and sets on the west, morning sun casts a tower shadow on the light sensor, as shown here. Afternoon sun may also cast a shadow on the light sensor in the afternoon. A better location of the light sensor is on the south side of the tower. How about the weather station installation in this picture? Here we see the wind speed, wind direction, and light sensor are all mounted on top of the tower with sufficient clearance from the building below. Next are a temperature and a relative humidity sensor mounted in aspirated radiation shield. Take 5 seconds. Look closely to see if there are something may need improvement. Okay, it is challenging to suggest any improvement without a better understanding of the surrounding of the weather station. Here are what I found. First, the temperature and humidity sensors are not that far from the building's exhaust vent. Second, the sensors are also adjacent to the building wall that may have influences on sensor readings. Third, there are trees nearby the sensors. Transpiration of the plants may affect sensor reading too. This is the end of this learning module on the topic of weather station for greenhouse production. Thank you for your viewing.